class number 2 of the Florida National University course of ultrasound physics. Propagation speed of ultrasound. Propagation speed is the speed at which sound or ultrasound moves through a medium. Looking that say through a medium, because ultrasound is a mechanical longitudinal wave, and mechanical longitudinal wave cannot move in through vacuum, need a medium, something material. This is something that we study in the class number 1. Propagation speed is a speed of the sound, is a speed of ultrasound, because sound and ultrasound are the same. The units that we use to measure the propagation speed of ultrasound is the same unit that we use to measure the propagation speed of anything. 1 unit of distance and 1 unit of time. The units for propagation speed are the same that we use commonly in cars. Distance, time, but the difference in car is miles, hour. In ultrasound we use millimeters, microsecond, but essentially it's the same. A unit of distance, miles, centimeters, and 1 unit of time, seconds, microseconds, any unit of time. Speed of the ultrasound in the medium is determined only by characteristics that are in the medium. You cannot change the propagation speed of sound of ultrasound. The propagation speed of sound and ultrasound is determined only by the characteristic of the medium the ultrasound goes through. And in the case of ultrasound or medical ultrasound, the medium is the tissue of the patient. The soft tissue of the patient is the medium where ultrasound goes through in medical ultrasound. We have something to explain this. We have 3 different materials: wood, steel, and soft tissue. And we have here three transducers with the same frequency, no different frequency, 5 megahertz, 5 million of hertz in 1 second, or 5 million of cycles in 1 second. And you can see here, when the ultrasound goes through the 3 different mediums, the propagation speed are different because they arrive at different times. Wood, steel, and soft tissue are 3 different materials. When you use the same frequency, different materials produce different velocities. Frequency is not related with propagation speed. In ultrasound we use different frequencies, always in megahertz, but we use different frequencies depending on what tissue we are working. If we are scanning kidneys, if we are scanning liver, if we are scanning uterus, that are organs that are at different depths, we use different frequencies. But the frequencies is not related with the propagation speed. The propagation speed is determined by conditions that are in the medium the ultrasound goes through, not in the frequency of ultrasound. You can see the same experiment with the same material. Ultrasound through steel. You can see here different frequencies, 3.5 megahertz, 5 megahertz, and 7.5 megahertz. This is typical frequency that we use in medical ultrasound, and you can see that even the frequencies are different, the propagation speeds are the same. Propagation speed of ultrasound do not depend on the frequency. propagation speed of ultrasound depend of characteristics that there are in the medium ultrasound goes through. What are the characteristics of the medium that determine the propagation speed of ultrasound? There are two. One is directly proportional, the other is inversely proportional. Density is inversely proportional. Density is the characteristic of the weight of the material the ultrasound is go through. A material that is more dense weight more. More dense is the material. Slow go ultrasound, in other words, are inversely proportional. Density and propagation speed are inversely proportional. The other condition of the medium that change the propagation speed is the stiffness, is how hard is the material. This is the reason I put there a diamond that is very, very hard. Stiffness is directly proportional. If you have more stiffness material, propagation speed is more, but density not. Density is inversely proportional. If you have more dense, the propagation speed is less. Inversely proportional, directly proportional. Density and speed propagation inversely related. You can see one arrow and the other arrow looking at the contrary direction. More dense is the material, less is the speed propagation. Of the contrary, stiff is the material, more is the speed propagation. In other, are directly related. Arrows are looking at the same direction. If the material is more stiff, the speed propagation is go faster or more, directly proportional. In resume, acoustic velocity of ultrasound or sound that is the same depends on the density and the stiffness of the material the ultrasound go through. But there are a little trick that they use in the examination. They don't use stiffness, they use plasticity or elasticity. That is the contrary of stiffness, and it's logical. If stiffness is inversely proportional, elasticity is inversely proportional. Propagation speed cannot be changed by the sonographer. It's a characteristic of the medium. You cannot change something in the body of the patient. The propagation speed depends on the density and stiffness of the soft tissue that is the medium the ultrasound go through when we are working with patients, human beings, soft tissue. The propagation speed in soft tissue is something that you cannot change. It's not operator adjustable. What is the propagation speed of ultrasound in soft tissue? The same propagation speed of sound in soft tissue, because sound and ultrasound are the same, are a mechanical longitudinal way. The velocity of ultrasound in soft tissue is something very important, and you must remember. And remember, repeat with me: 1, 5, 4, 0 meters by second. This is the most common question that they can ask you about propagation speed, but there are not other propagation speed of soft tissue, other presentation with different units. Here with the 1540 meter by second, that is the most common use unit to measure propagation speed of ultrasound. In soft tissue, there are other presentations. 1.54 kilometers over second. That is because kilometers have 1,000 meters. And that is for this you put 3 zeros or move the point decimal 1.54 is the same velocity that is 1540 meters by second. Only change the units. The units are changed, but the velocity are the same. And the most important velocity is this one, 1.54 millimeters over microsecond, because this is the measure of propagation speed that is better for calculation. And sometimes in the examination you need to make some calculation about the propagation speed of ultrasound. And when you use millimeters, this is more real in the human body than meters, because a liver cannot measure meters, can measure millimeters, is little. And microsecond have other advantage, that microsecond is related with megahertz. If the frequency is in megahertz, the period of the wave of the period of ultrasound is in microsecond. This is also an advantage when you make calculation about the ultrasound velocity in soft tissue. But remember, the most important, all the three are the same velocity, are not different, only have different presentations. You have here different tissues with different velocities, and you have also the soft tissue. Remember that the soft tissue is an average. It's the average between different organs that are in the soft tissue. You can see that bone is very fast because it's very stiff. Soft tissue 1.54 millimeters microsecond, millimeters microseconds. Very important. Fat is slow than long, is slower, and air that is very slow because it's very soft. Remember, soft is the medium, slow is the velocity, because stiffness and propagation speed are inversely proportional. Wavelength. Wavelength is a very important concept because wavelength is related with the quality, with the definition of the picture. Bigger is the wavelength, less is the quality of the picture. In other words, wavelength and quality, wavelength and definition are inversely proportional. Wavelength, of course, the unit of wavelength are a unit of distance. Wavelength is the length of the wave. The wavelength of ultrasound is determined by the frequency by the propagation velocity of the medium the ultrasound go through. Looking is the combination of the propagation speed of ultrasound and the frequency of ultrasound that you are using. All the two determine the wavelength of the ultrasound when have different frequencies. Why? Because the propagation speed is only one. The propagation speed of ultrasound in soft tissue. We can calculate different wavelengths with different frequencies because propagation speed is always to be the same. The propagation speed of ultrasound in soft tissue. Wavelength is the distance between the beginning and the final of one ultrasound cycle. Did you remember that I use in general in this horizontal, I use time, but in this moment is distance. Is the distance between here and here. But I prefer other explanation. The distance between the beginning of one compression and the beginning of the next compression from here to here. This is a better explanation than what is wavelength. Different frequencies, different wavelengths in soft tissue. Why? Because remember, we are going to always use only one propagation speed, the propagation speed of ultrasound in soft tissue, 1540 meters divided by second. Frequency and wavelength are inversely related, are inversely proportional. More is the frequency of the transducer, little is the wavelength, and this is good because little is the wavelength, better is the quality of the picture. And in ultrasound, that you are looking for is give the more quantity of quality to the medical doctor can make a good diagnostic of the patient. In other words, transducer with good frequency, transducer with high frequency like 7 megahertz are good for quality because the wavelength is little. Inversely proportional, the wavelength and the frequency. More is the frequency, little is the wavelength, and little is the wavelength, also better is the quality of the picture. You have here the formula of the wavelength. This is a very important formula. This is something that you must remember, that you must understand very, very good. Wavelength, that is the item that we are studying, is equal propagation speed 1540 meters over second, and the frequency of the transducer that you are using, 3 megahertz, 5 megahertz, 7.5 megahertz, depending on what organ you are scanning. But always higher is the frequency, little is the wavelength, and when the wavelength is little, the quality also is best. This is the formula with the Greek letters. Wavelength is equal velocity divided by frequency, and this is the name wavelength, speed of the ultrasound, and the frequency of the transducer. You can see other presentation of the formula. Frequency is equal velocity divided by wavelength. This is logical. And the other one, velocity of ultrasound is equal to wavelength multiply frequency. This is only easy mathematical. But there are questions in the ultrasound examination that try to look in if you know how to change the difference part of the formula. And this is for that you must understand the formula, but the most important part of the formula is that the wavelength is equal propagation speed over frequency of the transducer. Attenuation is very important. And I put a picture of ultrasound because it's supposed this patient have a fatty liver with a lot of attenuation, and the ultrasound cannot go through the liver. To explain you, this is the liver, this is the kidney, this is the liver, but the ultrasound cannot have enough penetration to go through the liver, and you can see one part of the liver is without ultrasound. Attenuation. Attenuation is the weakening of the sound wave as it travels in a medium. In other words, attenuation is the weakening of ultrasound wave as it travels in a medium. You can see that in this area here we have distance, and in this area here we have acoustic variable or amplitude. You can see at the beginning the amplitude is bigger, and when the wavelength is moving, the amplitude becomes little and little. And this is the same when you are talking with a person that is very far from you. You cannot hear good the person because the sound as ultrasound suffer attenuation when moving through the medium. In the case of medical ultrasound, is the soft tissue of the patient. The unit of attenuation are called decibels. We're talking about decibels in the last class. Decibels are measured to compare two numbers. In this case, to compare the amplitude at the beginning with amplitude more inside and the distance that the ultrasound moving. More is the distance, more is the attenuation. The unit of attenuation are negative decibels. Negative decibels. The unit of attenuation are negative decibels. And you have here the decibel. The most important decibel that we are going to use is the decibel 3 negative decibel, that mean the half. 3 negative decibel, that mean the half. Attenuation is determined by the frequency of the sound and by the distance the ultrasound moving inside the soft tissue. More is the distance, more is the attenuation. More is the frequency, more is the attenuation. In other time, both are directly proportional. Distance is directly proportional to attenuation, and distance also is directly proportional to attenuation. The two characteristics that determine the different attenuation are frequency and distance. More is the frequency, more is attenuated ultrasound. In other words, faster the ultrasound become weak. And this is the disadvantage of the high frequency. High frequency suffer too much attenuation, and high frequency have low penetration. In other words, with high frequency transducer, you cannot go very deep inside the body of the patient. High frequency have good quality, but are good for superficial organs like thyroid, that is very easy, breast and testicles, but for scan kidneys, sometimes the frequency is not enough to go deep. Frequency and attenuation are directly proportional. More is the frequency, more is the attenuation. But remember that change is the amplitude of the wave. The frequency don't change with attenuation. Frequency is always the same. One sound can be attenuated. When one ultrasound is attenuated, the amplitude change, but the frequency remain the same. This is very important because frequency and attenuation are directly related, but frequency do not change. That change is the amplitude of the wave. The acoustic variable of the wave change when it's attenuated, but the frequency remain the same. Distant attenuation also directly proportional. More is the distance that the ultrasound or the sound moving through the medium, more is the attenuation that the ultrasound suffer. In other words, the amplitude is less, the amplitude reduced with more distance when the ultrasound moves through the tissue. Attenuation is the conversion of ultrasound in heat, because you remember the first law of the energy. The first law of the thermodynamics say that you cannot produce energy, you cannot destroy energy. Energy change from one form to the other. The energy that is in the ultrasound when suffer attenuation is converted in heat, and this is called absorption. Absorption is the change of the ultrasound energy in heat, and this is the most important cause of attenuation, not the only one, because scattering, refraction are other cause of attenuation, but the most important cause of attenuation is absorption, the transformation of ultrasound in heat. Also, there are attenuations when the ultrasound is bouncing and moving to different parts. This is different than the attenuation of absorption. The ultrasound is not changing in energy, the ultrasound is changing in direction. And when changing direction, the ultrasound cannot return to the transducer. This is the scattering that produces attenuation, because the direction of the ultrasound change when there are scattering. Scattering is very important. We are going to talk more about scattering, because the characteristic of the structure is more produced by scattering, by other reflection of the ultrasound. Rayleigh scattering is a very important form of scattering. That happens when the ultrasound goes through the red cells. When the ultrasound goes through the red cells, change the direction, and this is called Rayleigh scattering. But remember something very important in RDMS ultrasound test. All these things that have the name of one person are common questions. Rayleigh scattering is a special form of scattering that occurs when a reflector is much smaller than the sound in the body is produced by the red cells. Remember, Rayleigh scattering is related with red cells. The attenuation coefficient is the quantity of attenuation that suffer ultrasound as travel 1 centimeter of soft tissue, and this is calculated in this formula. Attenuation coefficients, unit decibels divided by centimeters, is equal the frequency divided by 2. This is something very important that you know. This is not a physical formula. This is something that happens by causality only in soft tissue. Only in soft tissue, not in other material. But it's very good and it's very practical. The attenuation coefficient of ultrasound is the frequency divided by 2. But remember, when you divide by 2 megahertz, you also have megahertz. And here the answer is decibels centimeter. In other words, the units of attenuation coefficient are not the same unit of frequency. And this is for that. This is by causality. This is not a physical formula. It's something that happens and is very practical. The attenuation coefficient of ultrasound, when it's traveling through soft tissue, is equal the frequency of the transducer divided by 2. No physical, practical. First problem that is very easy to resolve. How much is attenuated a transducer of 7.5 megahertz when travel through 2 centimeters? The first thing is calculate only 1 centimeter. 7.5 divided by 2. But if the problem is asking you 2 centimeters, you need to multiply by 2. If you multiply by 2, 2 and 2, and it's the same 7.5 decibels. Decibels, not megahertz, because attenuation is not measured in megahertz. Attenuation is measured in decibels, and this is for that I told you that this formula is practical, is not physical. I am going to repeat how much is attenuated a 7.5 megahertz transducer when travel through 2 centimeters. To calculate 1 centimeter, 7.5 divided by 2. But they asking you 2 centimeters, you multiply by 2, 2 and 2 disconnect, and you have 7.5 decibels. The half value layer sickness is a complex concept. We need to put attention to understand what is the half value layer sickness. It is sickness of the tissue required to reduce the intensity of the sound beam by 1/2. Remember that 1/2 is equal 3 decibel negative. In other words, the half value layer sickness is the sickness of tissue required to reduce in 3 decibels the intensity of ultrasound. How calculate the half value layer sickness? This is the formula. To calculate the half value layer sickness, we need first to calculate the attenuation coefficient. You remember how to calculate the attenuation coefficient? I talking that the attenuation coefficient is calculated from the frequency, dividing by 2 the frequency. In other words, we calculate first the attenuation coefficient and we divide 3 decibel between the attenuation coefficient. 3 decibel, remember, 3 decibel mean the half. 3 decibel mean the half, exactly like 1/2. 3 decibel negative. Half value layer sickness, 3 decibel divided by the attenuation coefficient. Okay, go to the problem. What is the half value layer sickness of a 5 megahertz transducer? A 5 megahertz transducer is a transducer with a frequency in the middle. It's not a high frequency. It's not a low frequency. It's in the middle. 5 megahertz. Okay, first of all, we take and we get the attenuation coefficient for a 5 megahertz transducer. Attenuation coefficient for a 5 megahertz transducer is equal to 5 divided by 2. In other words, 2.5. We get the 2.5 and we make the division between 3 decibels and attenuation coefficient, and that give me 1.2 centimeters. In other words, a transducer of 5 megahertz need to travel through 1.2 centimeters to be attenuated 3 decibels. In other words, a transducer of 5 megahertz need 1.2 centimeters to be attenuated the half. We are going to do the same for a transducer of very low frequency, 2.5 megahertz. What is the half value layer of sickness of a 2.5 megahertz transducer? We are going to do the same. We take the frequency of the transducer and divide by 2. Frequency of the transducer divided by 2 is equal 1.25. This is the attenuation coefficient. We take the number 3 decibels and we divide by the attenuation coefficient and we have 2.4 centimeters. That means that A transducer of 2.5 megahertz need 2.4 centimeters to be attenuated the half, or to be attenuated 3 decibels. We are going to make the same in a high frequency transducer. What is the half value layer thickness of a 7.5 megahertz transducer? Very high frequency transducer. So we are going to do it the same. We take 7.5, the frequency, we divide by 2, and we get the attenuation coefficient. We get the attenuation coefficient and we divide 3 decibels between the attenuation coefficient and give me 0.8 centimeters. In other words, a transducer of 7.5 megahertz need only less than 1 centimeter to be attenuated the half. A transducer of 7.5 megahertz only in 0.8 centimeters is attenuated to the half. And this is the important part that I want you to see. The half value layer thickness is inversely proportional to the frequency of the transducer. The low frequency transducer have a high half value layer thickness, and the high frequency transducer have a low half value layer thickness. Half value layer thickness is the penetration. When a transducer have a big half value layer thickness, means that the frequency penetrate the body. When a transducer have 7.5 megahertz, mean that the penetration of high frequency transducer is not as good, is not as big as the frequency 2.5, and this is the reason that even transducer of high frequency have good quality, have not enough penetration to scan organs that are deeper in the bodies. In resume, 7.5 megahertz is good for thyroid, 2.5 megahertz is good for deeper organs like kidneys. Frequency and attenuation are directly proportional. Higher is the frequency, more is the attenuation that suffers the ultrasound. In other words, high frequency transducer have high attenuation, in other words, low penetration. High quality, high attenuation, low penetration, cannot penetrate deep organs. Attenuation and half value layer thickness are inversely proportional. More is the attenuation, less is the half value layer thickness, and this is the reason high frequency transducer have a high attenuation but have a low half value layer thickness. Frequency and half value thickness is inversely proportional. More is the frequency, less tissue must travel ultrasound to be attenuated the half. Repeat, more is the frequency, little is the half value layer thickness, because when the frequency is high, only in a little distance the ultrasound is attenuated the half. Attenuation and penetration is logical that are inversely proportional, because attenuation and penetration are the contrary. If something is too attenuated, cannot get good penetration. Frequency and penetration are inversely proportional, and this is the most important here. More is the frequency of the transducer, more is the frequency of the transducer, less is the penetration of the transducer. Frequency and penetration are inversely proportional, and this is for that the transducer with high frequency that have good quality are not good for deeper organ like the kidney, like the aorta. And high frequency transducers are good because have good quality pictures and are good for superficial organs like the thyroid, like the breast and the testicles. A new concept, impedance. Impedance is very important concept because impedance is the physical characteristic of a medium that produce the reflection of ultrasound. And the reflection of ultrasound is very important because the picture or the image that produce the machine are with the echo, with the ultrasound that is reflected in the body. Ultrasound go through the body, is reflected and produce the picture that we see. And this is for that it's very important to understand the concept of impedance. Impedance is the acoustic resistance to sound traveling through a medium. Resistance is similar to the electrical resistance, but this is mechanical resistance. Impedance is the acoustic resistance to sound traveling through a medium. Impedance is determined only by the characteristic of the medium. You cannot change the impedance. The impedance is the body, like the propagation speed. It's a characteristic of the body. You cannot change the impedance of any structure because are things that are in the body. Impedance is not operator adjustable. Impedance is only determined by the characteristic of the medium. In this case, soft tissue, because we scan soft tissue. The unit of impedance are very important to remember, are called rails. Rails is the unit of impedance. Sometimes in the examination, they want you make little calculation that use impedance. The definition of impedance, the most common, not the only one, is the density times the propagation speed. That means the impedance. Remember that the density is something that is the weight of the material, and the propagation speed is the velocity of ultrasound in soft tissue and is determined only by the medium. Density is a property of the medium. Propagation speed also is a property of the medium. In other words, we can conclude that impedance is a property of the medium. It's not operator changeable. It's not operator adjustable. Impedance, like propagation speed, is inside the body. You cannot change the propagation speed and you cannot change the impedance of the tissue in the body of the patient. Impedance cannot be changed by the sonographer. It's not operator adjustable. And this is for that we study impedance, because the most important phenomenon of ultrasound is the reflection, because the reflection is the information that produces the pictures in the monitor. If there are no reflection, if there are no echoes, there are no ultrasound image. Reflection is the most important physical phenomenon in the production of medical ultrasound. There are other uses of ultrasound that are not diagnostic, but in diagnostic ultrasound, reflection is the most important characteristic because it's the characteristic that produces the picture. It's the origin of echoes, and the echoes produce the pictures. There are three things that we must remember. What is an acute angle? What is a right angle? Remember, 90 degrees right angle. And remember, obtuse angle. Different angle. The most important for us is right angle, because to get reflection from the transducer, the reflection must have 90 degrees angle. Normal incidence, right angle, 90 degrees. This is a condition of the reflection to return to the transducer. It's very important that the reflection that the body produces coming back to the transducer, and this is for that it's very important to have a 90 degrees incidence. Normal incidence is the same as right angle and 90 degrees angle. Oblique incidence is not good because when you have oblique incidence, the reflection don't coming back to the transducer. There are reflections with oblique incidence but are not good because don't going back to the transducer. Okay, this is to begin understanding what is the reflection. This arrow is the ultrasound moving. The ultrasound is moving in the tissue and nothing is happening. In one moment, this is called incident intensity, and looking at the incident intensity is at 90 degrees. When the ultrasound goes through two different mediums, 1 and 2, a reflection is produced. The ultrasound, some part of the ultrasound remain in the same direction, some part of the ultrasound return. This ultrasound that return is called echo. This is the echo. The echo is produced when the ultrasound passes through two different mediums with two different impedances. This is reflected intensity, also called echo. And this is the transmitted intensity, that is the same ultrasound that remains. We are going to take other time the same thing. You can see how moving back and the other go away. Medium A is very important that there are two different mediums to produce a reflection, medium A and medium B. The ultrasound is moving, you know, the ultrasound gets the boundary between the two mediums, one echo was produced and the ultrasound continues. The boundary between two mediums with two different impedances is the place where the reflection occurs. The reflection is produced in the boundary between two mediums with two different impedances. Different impedance between the medium are needed to produce reflections, echoes. Repeat, is very important to remember this. Different impedance between the mediums are needed to produce reflections, echoes. The echoes are the information to produce the pictures, and the pictures are important to produce diagnosis. Incident intensity 100%. Of course, the sum of the reflected intensity and the transmitted intensity is 100%. This is the law of the conservation of energy, of First law, that say you cannot destroy energy, you cannot produce energy, you can change one energy in other form of energy. Is the reflected intensity is summed with the transmitted intensity is the same as the original frequency. We have some unit here to remember: velocity, distance over time, frequency, hertz, wavelength, distance, impedance, rails, and this is the unit that we must remember. Remember, examination and multiple choice, and in multiple choice examination, remember the units of the different items or different factors in ultrasound is very important. Impedance unit are rails. This is the explanation of the formula to calculate the reflection. It's called reflection coefficient. Impedance of medium A, impedance of medium B. Impedance of medium A is C1, impedance of medium 2 is C2. This is the formula. Sometimes in the examination have multiple choice question with this formula. It's the exception because in the examination really there are not too much formulas. The trick here is that the number that they are going to use are very easy and you can make the calculation if you remember to get the square. In other words, it's good to remember because even the question sometimes is easy, you need to make some mathematical calculation. Remember, don't use too much time in only one question. Multiply only the number, looking for the units, looking for everything that led you the answer. Sometimes it's not necessary to make calculation to know what is the correct answer. But if you need to make the calculation fast because it's not good deal to spend too much time only in one question. More than 1 minute in one question sometimes is not good deal. And a question like this with mathematical operations, sometimes you need more than 1 minute to do it. If two impedances are equal, can echoes be produced in the boundary? No. No echoes can be produced if the two mediums are equal. If there are not a mismatch in the impedance, there are no echoes. Echoes was produced when the ultrasound traveled through two different mediums with two different impedances. No echoes can be produced if the impedance between the two mediums are the same. Intensity reflection coefficient 0%, no reflection. Y. Two C1 minus C2 divide by C1 plus C2. Is C1 and C2 are the same? 0. 0 divided by anything is 0. 0 squared is 0. In other words, when the impedances are equal, no reflection was produced. Is very different than reflection. Reflection is the most important characteristic of ultrasound that help to produce picture. Refraction not. Refraction produce artifact. Refraction produce loss of quality. Refraction produce bad information. But it's important to know refraction, and it's very important to know that are different because in the examination a lot of time try to confuse you between reflection and refraction. Refraction is a change in direction. This is very important, a change in direction of a wave traveling from one medium to another and does not occur with normal incidence. Does not occur with normal incidence. Remember that normal indices is 90 degrees. Refraction is a change in the direction of a wave traveling from one medium to another with different propagation speed and does not occur with a normal incidence. Do not occur when the incidence of ultrasound is 90 degrees. Refraction only happens if the propagation speed between the two mediums the ultrasound go through are different, and refraction occurs only if the incidence angle is not 90 degrees. At 90 degrees, not refraction happen. You can see what happened with refraction. The angle of incidence is supposed to continue, but not is a change in the direction of the ultrasound when passed through a boundary between two mediums with different propagation speeds. You can see that the transmission angle and the incident angle are not the same. The angle changes here. There are a change in the angle, but not when the direction is 90 degrees, only when the angle is different at 90 degrees. If the propagation speed of the medium 1 is greater than the propagation speed of the medium 2, the change of direction go to the center. At the contrary, if the propagation speed of the medium 1 is less than propagation speed of the medium 2, the change of direction is far from the center. This is a typical question in RDMS. This is called the Snell law. Remember, all the things that have the name of one person are probable questions in RDMS. The Snell law say that the relation between the angle of transmission and the angle of incidence is equal the relation between the speed of the medium 2 and the speed of the medium 1. And okay, this is the end of the class.